There aren't that many classes left. Let me review what's on my mind as far as what we're going to do. I probably will not be able to finish Wavelet packets and Walsh functions tonight. But we shall. And then finish it. But what is today's the 11th, so next week is the 18th, so this is 11/11 Veterans Day. 11/18. I wanted to have one of the hottest topics these days is compressed sensing, and so I wanted to have at least one lecture on compressed sensing. So we'll do that next week. And in all honesty, I'm still learning the subject, and so I thought I'd have someone who knows a lot more than I tell you about it. So I'm going to have Matt Hearn give next week's lecture. He, as I say, he knows a lot more than I do about compressed sensing. And then 11:25, we'll, depending on where we are, we'll finish the Walshes, if we don't tonight. But then we'll start D-dimensional wavelets. And that's a subject one can spend a lot of time on, but given the fact that we don't have that many lectures, namely, that's a Monday night. And it's going to be in 1310. I mean, I could talk all about on D-dimensional wavelets, but maybe I'll pick another sort of more current topic for the last lecture. I haven't quite decided what I'll do. Okay? I mean, I really like these wavelet sets. And, or something else. Okay? And everything is due on the 9th. Okay? All the homework and all the projects. Because I'm going out of town on the 10th. And, okay? And I'll be taking that stuff with me. Now, before class, Brent brought to my attention these problems that we had with, there was a series of problems where we were looking at bases for L1. Remember, we were talking about the hash system. And, well, I made I'd say, a serious typo on posing one of those questions, and Thomas, who unfortunately is out of town now. Is someone trying to get in the door? Or
no.
Someone is? Oh. Thomas won't be here the next 2 weeks, unfortunately, but he is, on his typed notes, which I guess are also available on the website, corrected me. And so the question, it's number 27 in the exercises, I believe, and the question is to show, it asks, is the sequence a basis for L1 of R? In fact, ask it for any LP space where the psi MNs, psi MN is the pi system for L2 of 0, 1. So So that's what that should be. And also, I mean, that's the critical thing. There are some other issues in that, but that's the main problem here. Remember, there were constraints on the m and the n when you're just on 0, 1. But this is k goes through all of z.
John, you wanted me to remind you to get a hold of Enrique about the second?
Yes, but I guess I've decided you people will be working your problems and things, so maybe this will just be it. I won't have a. I was thinking of having another lecture on the second, but unless there's a wave, a wellspring of enthusiasm for 2 lectures that week, we'll skip it. Okay? Do I sense it? Do I feel the waves in the air?
Just wavelets.
Just wavelets, yeah, little waves. Okay, so let me talk about wavelet packets. And as you may recall, we had a very technical lecture where I essentially filled in the tree. And if we're given an MRA, a lot has happened since we last spoke to each other as far as politically speaking, and I'm not stupid enough to make any political statements, but it turns out I went to, in public, I went to Chicago I had to give a talk, and the place I gave the talk was at, I don't know Chicago very well. We were in a very lovely area, Michigan Avenue, near the lake in Chicago, and we went to an Italian restaurant which had a function room. It was a very fancy Italian restaurant, and that's where the meeting was held. It was called Spiaggia. I recommend it food-wise. In any case, we found out that 3 weeks earlier, President-elect Obama and his wife celebrated their 1620 wedding anniversary there. So that's the whole story. Here we go. So given an MRA, BJ, and and remember we did the bit reversal and all that stuff. We form the tree X, R, M, and R stands for the level. Where M goes from 0 up to 2 to the R minus 1. And X, 0, 0 is equal to V0. I'm not going to do all the motivations that I gave last time, but there was this urge to fill up the tree. That's what we did last time. Then each element X, Rm of the tree is a closed linear subspace of D0, and further, each X, R, M, R bigger or equal to 1 is determined by the function now I'll write it up here. The square root of 2, let me say, is determined by the function theta with epsilon 1, epsilon r, where square root of 2 to the r, theta hat epsilon 1 epsilon r of 2 to the r gamma is equal to phi hat of gamma, and then the product of these filters that come from the MRA, namely h epsilon 1 of gamma, h epsilon 2 of 2 gamma, all the way up to h epsilon r of 2 to the r minus 1. Yeah. And the epsilons are related to m in the following way, where m has a dyadic expansion, j equals 1 to r, epsilon j 2 to the j minus 1. And the epsilon j's are going to be 0 and 1. And it's determined in the sense that, x m is the closed linear span, in that way, of, when I take the inverse Fourier transform, I get the dilation the other way. Right? So I have 1 over the square root of 2 r theta of epsilon 1 epsilon r. I'm going to make a point of not writing this 12 times tonight, so let me get it down to 1 time. T over 2 to the r minus n, where n is in z. So it's the span of that guy. And these guys here and these form an orthonormal basis for x, r, m. And not only that, and we're going to be able to write down that d0 is actually equal to the orthogonal complement direct sum from m equals 0 up to 2r minus 1 of all of our guys dx. So that's what we proved. And that's the result. And we actually get some other things out of it for, there are no free lunches, but in this case we do get a little bit more out of this, because what we really also did was, so we filled in the tree. That is to say, we started with V0, and then by MRA we knew how to do this, V minus 1, W minus 1, and by MRA we knew how to do this, V minus 2, W minus 2, but then we were stumped. So this was level 0, this was level 1, then at level 2, we just called it x2, and then, I don't know, if this is x, it's going to be an m. And this is when we got into bit reversal, another m. And then we had level 3, and we're able to figure out that a reasonable way of defining these x's was in this way here. I mean, that was the content last week. Now, when we have this tree, if we stop, I mean, and they obviously, there's a doubling process here. There are 2 elements here, 4 elements in here, 8 elements in here, 16 elements here. What this result says, so this is 0, 1, 2, and 3. What this result asserts here is that if I take all of the fees corresponding to each of these nodes here, and then look at all of those fees corresponding to the bottom line nodes, and do this with it, those form an orthonormal basis for V0. Okay? But what we get for free is the following. What we get for free is that I don't have to just take the bottom lines in. I can take this one and this one, okay? And then I have to make sure I cover everything up here, but I can take some others over here. So I have this concept that I call the hemline, where you can look at instead of looking at a line like this, I can look at a line, and this line would correspond to looking at all of these circles. I can take other as long as I'm covering the parents. Okay, so I'll go into more detail about that, but that's the concept. Okay, so now what is the next step? Well, these products of filters are sort of interesting, and so what we're going to look at is the following. I want to illustrate. I mean, it's more or less intuitively apparent, but I want to illustrate how diverse the frequency structure you can get this way is. And it's a matter of how much chalk I decide to use here. Maybe I'll skip some of the actual details, although I've done all of them. But let's first of all, let's call these things here frequency symbols. Okay. Frequency symbols. And if we just look at an MRA first, then what we have is the following. So consider an MRA not the wavelet packet situation. So if we consider an MRA and not the wavelet packet situation, I'm making choices here to throw away things just to spare too much pain. What we have is, if we do the calculations out, for M fixed, but these are things you can all do as exercises or just from the MRA structure. We have that psi minus Mn, and that's the wavelet that we get from the MRA, at T, which is equal to, as we know, 1 over the square root of 2 to the M psi of 2 to the minus mt minus n. These guys here is, that set is an orthonormal basis for W minus M, which is equal to X1 M. And this was not very pedagogically good as far as board work goes, but that X1 M is you're at the mth level. It's the second space in, right? I mean, the first one is X0 M, and then so that's just something we know. That is directly from the basic wavelet, MRA wavelet theorem. And similarly, if we look at for a fixed M, also X M0 is equal to V minus M, where this set here, phi minus M N T equals 1 over the square root of 2 to the M, phi of 2 to the minus M T minus N is an orthonormal basis for V minus M. Because this, at the mth level, this is the first subspace of the tree as you're going from left to right. That tree that I just had. Now, if we write this out, which we did in the MRA theorem, we have, note, we know that 2 to the M over 2, phi hat of 2 to the M gamma is equal to phi hat of gamma H0 of gamma H0 of 2 gamma all the way down to H0 of 2 to the M minus 1 gamma. Okay, now we, at the time I did the MRA theorem, we could have written that down, but that's a special case of what we proved over here. It's just that when you're at the zero, if you're at the nth level, and you look at this space at the nth level, the first space, and you're going left to right, then if you write out what phi hat of 2 to the M gamma is, that's what you get. You get all zeros. That's the whole point. And that we could do with the MRA theorem. This didn't require us to do anything fancy as far as the wavelet packet algorithm that we did last time. I mean, I haven't defined what a wavelet packet is, so that thing I did last time, which I encapsulated here, which is going to be calling the wavelet packet algorithm. Well, if we, it turns out, I misplaced my notes, but if we did this with the size, what you get is, with the size you get similarly, bad sign when you replace your notes so early in the lecture. Similarly, you get 2 to the M over 2 psi hat of 2 to the M gamma is equal to phi hat of gamma, and then H0 of gamma, H0 of 2 gamma, all the way down to H0 of 2 to the M minus 2 gamma times H1 of 2 to the M minus 1. Yeah. So what I'm saying there is that when we draw the tree, and I don't need the wavelet packet algorithm, just looking at the simple old tree that we get from the MRA, if we have this situation here. Right? That's the MRA partial tree. And all I'm saying is that if I'm at level M here, and I write out the frequency symbol for level M for this node, that's M0, and that's XM1. And this guy here, this is the M-1 level. This is XM minus 1, 1. Of course, this is really V minus M and W minus M. And this is really W minus M minus 1. And that means that, and as I say, that's a special case of that calculation, but we could have done it at the time we proved the MRA theorem. But that means the following. That means that in the case of, let's pick a level that I can compute easily. So let's just look at the at level 2. So when I'm at level 2, and let's take, for convenience, for example, the Shannon Wavelet, MRA Wavelet. And in that case, H0, then H0 is equal to the characteristic function minus 1/4, 1/4. And of course I need a, just leave it there for a second, Mark. I have to have a square root of 2 up front here. Okay, we've done those calculations out. And then when I write out H1, H1 is actually going to be, I'm going to put quotes around it because I pick up an exponential in there. But let's just make believe there's no exponential there since it does not affect what I'm going to say about frequency. So H1 is really just, is equal to the square root of 2, then 1 minus the characteristic function minus 1/4, 1/4 on minus 1/2, 1/2 defined 1 periodic. And this, of course, is also defined 1 periodic. Now, so that we don't, I'm going to repeat myself here. So we don't have, this is the spirit of what's happening. There is, in fact, an exponential here, but that does not foul anything up as far as the picture I'm about to draw. Because in the picture, what happens is we're on minus 1/2 to 1/2, and there's a 4th, and there's a 4th. And so H0 looks like that, a low pass filter, and everything's defined 1 periodically, whereas H1 looks like this, except for this 1/2, 1 minus a 4th, 0, 1/4, 1/2, And basically it looks like this. And that's a high pass filter. Okay? So for the Shannon wavelet, when we play the game and have the Shannon MRA, which we talked about, basically, and that's the sync function. The wavelet theory, the MRA defined by the sync function, which we've done in class. So this is H1. And so now what happens at level 2 when I see what the frequency symbols, what's going on with the frequency symbols? So, well, basically I'm going to get 3 pictures here. I'm going to broaden it out too. So I'm going to make -0.5 here and 0.5 over here. And basically that's going to be -1/4 and this is going to be 1/4. And so H1 of gamma is going to look like that. And I'm just covering up that part of the frequency domain. And why am I picking H1 of gamma? H0 of gamma? No, H1 of gamma. I'm picking H1 of gamma because at level 2, that's 2 to the 1. Oops. Why am I doing this here? Well, that's certainly true what I wrote, but I want to get H1 of 2. Oh yeah, I want H1 of 2 gamma. So that means that, so this is H1 of gamma. And so if I look at H0 of gamma times H1 of 2 gamma, and that would be the symbol that I would pick up from the side, as to say that I would pick up here. What we get is, I've got this as a characteristic function from -4 to 1/4. And then this is squeezing this thing down by 1/2. And so when I multiply those two guys together, what I get is this. And so I'm going from 1/8 now. So this is 1/4, and this is 1/8 to 1/4. And similarly, I'm over here. That's 1/4. This is so badly not drawn to scale, it's unbelievable. In fact, it's
It's
can you do some scaling with your picture? No. So this is there's 0, and here's an 1/8, and this is unbelievable.
No, it's just the right-hand side is a little off. That
Yeah,
top,
the right-hand side is a little off, and I just don't feel like redrawing.
No, that top 1/4 is mislabeled, isn't it?
No.
No.
Oh, it is. Oh,
yeah.
you're right. Oh, thank you. Thank you. It wasn't so bad. So then, let me try that again then. Okay. Thank you. So I'm just bringing it down, and I'm going to 1/8 then to 1/4. Thank you. Okay. Okay? And then, if I look at H0, so I have H0 of gamma, H0 of 2 gamma. then, of course, that has its support in minus a fourth to a fourth. So this has its support in minus an eighth to an eighth. And it's zero elsewhere, so the one periodicity doesn't affect things. And so here I am now, I've got this from minus 1/8 to 1/8. And now notice, having H1 drawn here is not only helpful to have made this choice here, but H1 is exactly what is associated with this guy here for the case m equals 2. So when m is equal to 2, let me draw it instead of crowding it in. So m equals 2. What I really have then is V0, V minus 1, W minus 1, and then V minus 2, W minus 2. So I'm just doing MRA here. And so that means what I'm really associating is H0 of gamma, H0 of 2 gamma to that node. And I'm doing H0 of gamma, H1 of 2 gamma to that node. And I'm doing H1 of gamma to this node. So that's just on the frequency side of this MRA partial tree. And so all of a sudden I'm in a situation where, just by the definition of the MRA, I can't have a hemline that's actually straight across. I actually have to do a little bit of a bounce up here. And note what happens. So I'm really dealing with, this is at level 2, these two, but I can't have level 2 for all of them. I've got to go up a level in the MRA to this one. So what I've made is I've made a frequency decomposition at level 2, which per force I need to go up to level 1 for part of it, namely here, and then at level 2 I get this. So drawing that situation, what I have is the following. Here I am on minus a half to a half, and so it's minus 1/2 to 1/2, and there's a 0, and there's a fourth, and there's an eighth, and basically I get the frequency decomposition with this one here, which with the bit reversal numbering is 0, 0. And then I get, at also level 2, I get the 0, 1, 0, 1. And then, because there's no other level, no other node at the second level, I have to go up 1, as I did here. And this is 1 and 1. And so, if I want to think in terms of frequency symbols and how the frequency domain at a given level is played out, then it has to look like this if I do MRA. Now, this is for the Shannon because, first of all, those supports are very nice, and one notices one is getting a tiling of the frequency domain. Okay, so maybe I'm spending more time on this than I probably should have, but now if we the idea of, now let's look at the wavelet packet we get with the Shannon. And then if we look at the wavelet packet we get with the Shannon, maybe I should just write down what the result is instead of doing all these computations. But the wavelet, I'll just write WP wavelet packet. The wavelet packet frequency symbol decomposition for the Shannon wavelet is the following. So I'm still going to have, let me try to draw it underneath here. I'm going from minus a half to a half. The first two guys are still going to be the same. I mean, they're the same animals. I mean, the x 0, 2, and the x 1, 2 are still v minus 2 and w minus 2, respectively. So what I know for sure that's going to happen is if this is a 0, and this is a 4th, and this is an 8th, then I know that I'm still going to have the 0, 0 here. And I'm still going to have the 0, 1 here and here. And then what's interesting is, so this is an 8th, a 4th, and I'm just so, this is a particularly bad night as far as perspective. Huh? So let me just make this a blunt. That's not so bad. And so I'm here at minus an 8th. I'm here at minus 1/4. And I want to come out a little bit more here. So 1/8, 2/8, and this will be 3/8 here. And what I'm getting then there from the frequency decomposition, now that I have those other nodes in the tree, I'm getting, when I do the arithmetic out, I get a 1, 1 and a 1, 0. And those are the bit reversal. So I'm saying something obvious, and I think I'm saying it in a completely incomprehensible way. But basically, once we have this wavelet packet algorithm and can fill out the tree, then we have a natural way of looking at frequency decompositions. That is to say, if we want to do some sort of experiment, or we have some sort of design issue where we can where we know something about the types of frequencies we're dealing with, then we might be able to say, well, at a certain level I can do this. And so you get a much finer resolution of the frequency domain because of the wavelet packet algorithm. And that was the major intent of what I wanted to say. Well, I haven't really defined, I have not defined wavelet packets. What I did was I talked about filling out the tree, and I call that the wavelet packet algorithm. Now, I want to define something called a wavelet packet, and I want them to be, and this has a very big story line to it now, especially I think motivated by the work of Nair, Koifman, and Wickerhauser, and and also the fact that in 1923, Professor Walsh wrote this paper, which has had incredible implications, ramifications of what are now called Walsh functions, which is a special case of this. That there's a big story and we use the term wavelet packets to essentially mean objects, functions, in which to generate lots of orthonormal bases. Much farther on beyond what is done in MRA, and the fact that it ties together with, as I said, this sort of ancient story that comes from Haar and Rademacher and then Walsh is truly fascinating. So, I'm just going to, because of that, of wanting to come up with a word we're going to call wavelet packets that's going to give us a way of generating lots of orthonormal bases. I'm going to define wavelet packets in a cold-blooded way now, but highly motivated by what I just said. So let's go. So, now in some sense I don't need an MRA to do any of this. I mean, it's if I just have a bunch of filters, I can place part of the scheme. And of course, this was one of the things that went on, as I mentioned to you earlier, in the late 70s and early 80s with speech and image processing business. And then in the very early 90s, when some engineers rightly said, gee, well, we did all of this wavelet theory. It's very nice the way you've unified it and all that, but a lot of this has been done earlier. And it is true. A lot of it was, but wavelet theory itself, at the hands of people like Dobeschies and Mayer, and also groups in Austria like Birkenig and Feichinger, and groups in the United States like Jauer, who's Swedish actually, but also Fraser. People brought together a tremendous amount of other mathematics, which has had a beneficial effect on the whole theory. Okay, so what are we going to call a wavelet packet? Well, let H0, H1 be in L2 of the torus, and with Fourier coefficients H0 and H1 n respectively. Okay. A sequence WI, where I goes from 0, 1, etc., contained in L2R, functions is a sequence of wavelet packets if and they correspond to corresponding to H0 and H1 if W 2I of T is equal to the sum H0 n square root of 2 Wi of 2t minus n, and it converges at L2R. And W2I plus 1t is equal to the sum H1 of n square root of 2 wi 2t minus n. And so for any I will be the single parent of w2i and w2i plus 1. And this is going to work out very well as far as the way we set up the bit reversal and all the sort of stuff. And one of the things I want to think about, I want to think in terms of, so the point of view is the following. And I'm not sure if you're driving, I'm very driving, I'm going to get a sip of water. 10 seconds. What I think about it is, I mean, this was done with malice before thought. But we want to tie this in with our algorithm. We somehow want to, in the case of an MRA, we want to essentially say that W0 is phi and W1 is psi. Now, what happens with this tree is, I mean, we really just have the functions theta, epsilon 1 up to epsilon r for a given level r. And it's only when we do this type of translation and dilation that we get an off-and-on basis for theta of r m. But we really are just generating a sequence of functions. If you don't think about the dilation, we're really just generating a sequence of functions, theta, for any, so, excuse me, let me say it logically. So for any r, we're generating a sequence of 2 to the r minus 1 functions, ordered this way. And what we're really saying is that as r gets bigger, as I go with my hand down, it's looking a little better, as r gets larger but lower in the tree, what we want is, I'm going to be starting at that left node on the tree, and I'm going to, for a given r, I'm going to have 2 to the r minus 1 nodes. I want to associate with this node, the first one I want to associate W0, the next node W1, chug, 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 chug. The last node I want to associate with W of 2 to the r minus 1. But then if I take an even larger r, let's call it S, I'm going to have 2 to the s minus, at level s, I'm going to have 2 to the s minus 1 nodes. Well, I'm still going to start over here on my tree and have the first node corresponds to W0, which is the same W0 I've had all along, which is going to be phi if in an MRA situation. And then the second node is going to be W1, which is the same W1 I've had all along. And at some point we're going to get up to 2 to the r minus 1, which is going to be the same node as W sub 2 to the r minus 1. And then the next one is going to be W of 2 to the r, W of 2 to the r plus 1, all the way out to W 2 to the s minus 1. So I'm thinking of this as an infinite tree. And that's one of the reasons we're saying we're taking an infinite sequence here. But for any fixed level r, we're just going to be looking at the first 2 to the r minus 1. Okay? And not only that, what we're doing is we're going to be saying that the WK, say, will correspond to these thetas. I mean, this thing we call the Wavelet packet algorithm was called the Wavelet packet algorithm because it's going to tie in completely with the thetas here. I mean, with the W's. So that's the general theorem. Okay, and that theorem is a little raggedy to put all the details in, just because of the complexity of the notation and stuff like that. So one of the things I'm going to do is work out a couple of examples But before I do that, well, this is part of working on an example. Let's see, which one do I want to do? I think I'll take, hold on for 1 second. I guess I'll look at the higher MRA first. Okay. Did people understand what I just said, though? I mean, was I just talking to myself? Did you understand what I said, Ken? Everyone understand? Okay, so no. And let me try it once more, because basically what I want to do is I've made a cold-blooded definition, right? I start off with a couple of filters, and I make a cold-blooded definition. I went through a lot of work last time. I mean, it's not real work, of course. There are people who really work for a living, building buildings and whatever. But anyhow, I went through a lot of work last time to complete the tree. And what I'm saying is I want to tie these two guys together. They are the same, is the theorem. And how are they the same? They are going to be the same under certain cases that if I take my completed tree and I forget about the thetas now for a minute. But if I take that completed tree, which after all depended on H0 and H1 only, an MRA would feed. If I take that completed tree and then look at the nodes at any given level, I've got 2 to the R minus, at level R, I've got 2 to the R minus 1 nodes, right? And now I want to take W0 from my definition waiver packet, forget the theta for a moment, and associate it with the first node on the left of the tree. And then take W1 and associate it with the second node. And W2 and associate it with the third node. And then I'm going to run out of W's at the 2R minus first node. Okay. I've got an infinite number of those W's. I'm just saying if I take S bigger than R, I'm going to play the same game. I'm going to look at the first node and associate W0 to it, second node and associate W1, run all the way through up to 2 to the R minus 1, and that's going to be my W2 to the R minus 1. I still got a bunch of nodes here, and I'm going to continue adding them from my definition of wavelet packet until I get to W2 to the S minus 1. And I'm thinking of myself having an infinite tree, and so I've got an infinite number of these guys. Why would I want to do that since I already had omegas associated with those nodes? And, thetas rather. And the reason is they're the same under certain circumstances. When I have an MRA, that's the theorem. Did I say it more clearly now? A little bit. On a scale of 1 to 10, I get a 1.2.
All right, well, let me try then, or just ask a question. How do you go from the wavelet packets to an orthonormal basis?
Well, you're going to give me a break here because I didn't assume MRA did. I'm just talking formally right now. In the case, both times, what I said was, under certain circumstances, they're going to be the same. Here, I started off with an MRA, which gave me an orthonormal basis.
Uh-huh.
When I assume I have an orthonormal MRA over here, then I'm going to be able to get orthonormal bases in a way that I'll show you.
Okay.
Okay. Now, let's see. I'm looking at techniques. I'm looking at lots of calculations, which I don't want to necessarily do. Let me just say one thing, just so to make a little explicit the hand waving I just did. So, for example, we'll show, in the case of an MRA, say, let me get it right so I don't, we'll show that theta 1, 0 is equal to W2. remember that theta 1, 0 is the, when we did the bit reversal, we're at the second level, and the bit reversal numbering of going from 0, 1, 2, 3 is this is the third one, because of the way it went was at the first level it's 0, 1, and at the second level it's really 0, 2, 1, 3. Okay? And so I want to get 1 as the third element in the second level, and that's what that baby is. And that's the third element of the second level. So that's with the bit reversal, and that's just arbitrary numbering. Okay, and so, for example, we'll show that that equals that and much more. When, for example, we assume an MRA. Okay. And so, as I mentioned, there are lots of special cases. I mean, I can assume an MRA, in which case I've got two filters, H0 and H1, and the H1 and the H0 are related by their, for example, by their Fourier coefficients, where the H1, little h1 of n is equal to minus 1 to the n, little h of minus n plus 1, or depending on how you do the calculation. Or I can just start off with any old two filters. And you won't get as far, but there are ways you can proceed. But in the MRA case, I can do this completely. Now, and like I'm asking myself here, how much of these details I'm going to do. I'm going to put this aside because it does get pretty technical. And maybe I'll, for a moment, just can just start right in with the power MRA. So, for specificity, consider the power MRA. Now, in that case, the scaling function phi is just the characteristic function from 0 to 1. Right? And H0 has H little 0, excuse me, H little 0 at 0 is equal to 1 over the square root of 2 is equal to H little 0 at 1, and H little 0 of n equals 0 otherwise. Okay, we work all that out. And also, H1 was defined by H0 of 0 is equal to 1 over the square root of 2, and H0 of 1 is equal to minus 1 over the square root of 2, and H0 of n is equal to 0 otherwise. That's just repeating what we did when we worked out the MRA. And basically, if you write out, I mean, if we write out the trig series corresponding to this, what do we get? Well, the trigonometric series is that, therefore, H0 of gamma is equal to 1 over the square root of 2, and then 1 plus e to the minus 2 pi gamma. And of of course, that's a cosine. But you just, yes?
Did you mean H1 or 0 in the bottom line?
I certainly did, thank you.
Thank you very much.
So this is just the square root of 2. E to the minus pi I gamma cosine pi gamma. And then H1 of gamma is equal to, well, it's just going to be the same thing here with a minus sign there. 1 minus e to the minus 2 pi I gamma. And then here we get square root of 2I e to the minus pi I gamma sine pi. So those are the two filters, and one is, and this is high pass, excuse me, low pass, and this is high pass. And then we computed the orthonormal wavelet. I mean, I'm just, as I say, recounting what we did with the Haar system. Then we computed psi to be equal to the characteristic function from 0, 1, half, minus the characteristic function from 1 half. And that, in some sense, was the whole story for the Haar orthonormal wavelet. Now, let's look at this in light of definition of wavelet packets. So let J equal 0. Then W0 of t is equal to W0 of 2t plus W0 of 2t minus 1. Okay, so we've got, basically we've got two filters, but I'm using as those two filters the Haar filters. And I've put in the square root of 2 here so they cancel the one over the square root. And my sum here just has two elements in it. So we have that, and then we also have that W1, I have J equals 0, W1 of t is equal to W0 of 2t minus W0 of 2t minus 1. Okay. Just note that phi, if W0 equals phi and W1 equals psi, satisfies this equation here. Haar at J equals 0. I can't use that. Anyhow. Well, star. Star 0. Satisfies star 0. Now that's not necessarily the way to show off your mathematics. That's the way we frequently do our mathematics. We want to do a tuxedo sometimes. But that's true because if you just look at, here's what phi is, and then phi of 2t, well, I'm just crunching it up, I'm contracting it. So here I am at 1, and here I am at a half. Phi of t, phi of 2t. And then, if I look at phi of 2t minus 1, I get the other thing I want. I have 1/2 to 1, and I'm at 1 there. This is phi of 2t minus 1. Because since 2t minus 1, if that's in, the only time that's going to be equal to 1 is when it's in 0, 1. That is 2t is in 1, 2. That is t is in 1/2, 1. And it's 0 otherwise. So I'm just beating it to death. And so basically I'm adding those two guys with phi identically 1 there, and that first equation holds. So I've just observed, without proving anything, well, it's true, but I observed, that if I take phi, then because of the way phi behaves, it satisfies the first equation. And similarly, psi satisfies the second equation. Well, what we'd really like to do, we'd like to ask ourselves, are there any other solutions to these equations? Why not ask that? A cold winter night, so a little tumbler of a good whiskey, you ask yourself a question like that. So let's show why those are the only solutions. Okay, you've got Wavelet packets here. They're pretty straightforward definition. So I'm still going to leave that tree definition board up, but I shall erase this. Okay. Well, let's take the Fourier transform of star 0. So the Fourier transform, I have those equations, and the Fourier transform of star 0. So right off the bat, I'm not even necessarily assuming L1, but I'm assuming that I can take Fourier transform of these stuff. The Fourier transform of star 1 is W 0 hat of gamma is equal to 1/2, and then I have 1 plus e to the minus I gamma, and then W 0 hat of gamma over 2. Okay, so I mean, basically, in theory, you have to verify this, but I don't want to do out every detail. I think you'll believe this. Here I've got the Fourier transform of a dilation. I have the dilation times the original Fourier transform. And then here, I'm going to pick up an exponential because of the translation. So it's a perfectly meaningful discussion. And this is equal to what? Well, this is equal to 1 over the square root of 2 times h0. Let me write the w first. W0 hat of gamma over 2 times h0 of gamma over 2. Okay, because of what h0 is. H0 is just that 1 plus 1 over the square root of 2, 1 plus e to the minus 2 pi I gamma. So by dividing by 2, I get that guy. Okay, so now what? Punt. Well, one of the things we can do is, let's see what happens when we iterate. So, I mean, I've got a gamma over 2 there, so I can continue the game. So, so first of all here, I had to be able to take a Fourier transform. So anytime I can take a Fourier transform, this calculation is going to work so far. So continuing, iteration-wise, I get W0 hat of gamma. And let me just repeat what I had. Well, no, let's go 2 W0 hat gamma over 2 H0 gamma over 2. And that's equal to, and I want to write out, I'm not sure what I switched, I basically want to be the other way around. That's equal to, when I write out the W0 hat over 2, I get that's equal to 1 over the square root of 2 H0 of gamma over 2, and then 1 over the square root of 2 H0 of gamma over 4, and then W0 hat of gamma over 2 squared. Okay, so I can continue playing this game. This is equal to, this is sort of a fun game. Maybe adults shouldn't do it, but it's sort of a fun game. I'm hedging my bets that I'm not going to use that again. That's equal to the product J equals 1 n of 1 over the square root of 2 H0 of gamma over 2 to the j, and then W0 hat of gamma over 2 to the j. And that's equal to, well, let me just bring it out here. This is equal to W0 hat of gamma over 2 to the n. And now we know what H is. H is those cosines, right? H0. And so we have here the product from J equals 1 to n of e to the minus pi I. I've got that e to the minus pi I gamma. So I want to go with this gamma over to the powers, with the ends. So that's e to the pi I gamma over 2 to the j, and then the cosine of pi gamma over 2 to the j. Okay, now I've got to make a little bit of an assumption here. Let's ask for, after all, we're not really constrained to be so precise at the moment, so constrained. But we're not really constrained at the moment, but for the sake of calculation, let me say, so find solutions W0 in L1 of R. I'm taking a Fourier transform, such that W0 hat at 0 is equal to 1. Okay, I'm putting a Stilson wrench here because I want to let n go to infinity. And so, I guess that's all I need right now. Well, if I do that, this of course is the same as the integral of W. Well, if I do that, then if I take the limit as n goes to infinity, because the left-hand side doesn't depend on n at all, so we have that therefore W hat 0 of gamma is equal to, well, that just goes to 1, and this is equal to x of minus pi I gamma. And then I've got the sum, since I have a product, the sum from j equals 1 to infinity of 1 over 2 to the j. and then I've got a product of these cosines. Now, of course, that, we know how to compute that, right? That's just equal to 1. So this is equal to e to the minus I gamma sine I gamma over pi gamma. Now that formula there, that product is equal to that, is known as Viet's formula. It's an exercise, by the way, in my book. It's, and I give hints. As far as I remember, Viet was the code breaker for King Henry IV. So this is a long time ago, in the, I guess, the late 1500s. He didn't serve so long, but to complicate his life, he was a Huguenot and sort of ostensibly in a Catholic country. But anyhow, Viet was, I'm not sure what he was, except he was very smart. So, but hey, look what we did. We proved that if you have a solution in L1 that's normalized, that solution has to be, therefore, I mean, we can take now, that's the Fourier transform. We know that the sinc goes into a characteristic function, and here, that's just going to be a translator of it. That characteristic function is centered, and this is going to move it to the positive axis. So therefore, W0 is equal to T. Pretty neat, huh? It's natural to ask, are there any other, if you open up the Pandora's box here and consider larger classes, and basically, I wouldn't bet any of my children on this, but I did some calculations a number of years ago, and I believe it doesn't. This is the only solution. I mean, even if you start looking at distributional solutions and the like. So there you go. Now, what happens? So also we get similarly. Psi 1, excuse me, W1 can be computed to be the Howard by essentially a very similar calculation. Okay, now let's look at 7:30. I'm going to stop at 8:30. Should we take a 5-minute break now, or what do you think? If some people